The title of this video declares the end of aluminum, a statement that undoubtedly sounds dramatic, perhaps even a touch hyperbolic. Yet, by the time you finish watching, you will grasp precisely why we chose such an audacious claim, and you will likely find yourself nodding in agreement, because what Xiaomi has accomplished in the realm of automotive manufacturing is so profoundly disruptive that it renders conventional aluminum construction virtually obsolete, seemingly a relic destined for a museum. Now, envision this scenario. It's the year 2021. A technology company, then primarily recognized for its affordable smartphones, innovative air fryers, and popular electric scooters, steps into a high-stakes boardroom. There, they announce a bold ambition. We're going to build a car. But not just any car. They envision a vehicle capable of conquering the legendary Nürburgring faster than a Porsche, a car boasting greater structural stiffness than a Bugatti, and a chassis that would be printed, not laboriously welded, in less than 2 minutes per section. The room, predictably, erupts in laughter. Such claims from a tech newcomer seemed ludicrous. Fast forward 3 years and the laughter has ceased. The Xiaomi SU7 Ultra is not only a reality, it's a tangible vehicle on the road. It recently shattered expectations by completing a Nürburgring lap in an astonishing 6 minutes and 46 seconds, outperforming even the formidable Porsche Taycan Turbo GT by several precious seconds. But the most mind-boggling aspect isn't merely its blistering speed. It's the utterly revolutionary method by which it was constructed. Xiaomi didn't simply create another fast car. They audaciously discarded a century of entrenched automotive manufacturing traditions and initiated their entire process from a blank slate. This meant no conventional welding, no meticulous stamping of hundreds of steel pieces, and no reliance on massive, energy-intensive baking ovens. Instead, they leveraged cutting-edge artificial intelligence to engineer an entirely novel metal, one that had never existed before. To shape this groundbreaking material, they then constructed a colossal machine spanning the equivalent of 2 basketball courts. Finally, and most ingeniously, they transformed the car's battery pack itself into the actual structural skeleton of the vehicle. The resulting design is so radically different from anything currently on the road that its specifications read almost like a fantasy datasheet from a video game. Yet, every single number is real. Every claim substantiated by the advanced machinery already operational in their Beijing factory today. By the conclusion of this discussion, you will understand exactly how Xiaomi achieved this monumental feat and why the established automotive world is now frantically striving to keep pace. Let's begin at the very genesis of the problem, the fundamental flaw in every car ever made. Here's an observation most people rarely consider. The fundamental method for building cars today remains remarkably similar to how they were constructed back in the 1950s. The process typically involves taking flat sheets of steel, stamping them into various shapes using enormous industrial presses, and then meticulously welding all those individual pieces together. This assembly often entails hundreds of distinct pieces and thousands of separate welds. It's a methodology that has persisted for generations. Imagine it akin to assembling a cardboard box. You cut out all the flat panels, fold them into the desired form, and then secure everything together with tape. While functional, every single fold introduces a potential weak point. Similarly, every piece of tape represents a location where structural integrity could eventually fail. Furthermore, the greater the number of individual pieces involved, the heavier and inherently more complex the entire structure becomes. In a car, each weld point represents a potential point of failure or fatigue over time. A standard car chassis can incorporate hundreds of individually stamped parts, interconnected by hundreds or even thousands of welds. Each one adds unnecessary weight, contributes to slight vibrations, and provides an avenue for unwanted noise to permeate the cabin. For decades, engineers have painstakingly shaved off grams here and there, striving to make the process incrementally better and cheaper. However, the fundamental underlying concept has remained steadfastly unchanged. Then, the advent of electric vehicles arrived, exacerbating this inherent problem even further. An EV, by its very nature, must accommodate a massive, extraordinarily heavy battery pack. This substantial battery needs a place, and the floor directly beneath the passenger cabin presents the most logical, albeit challenging, location. However, simply bolting a colossal battery box beneath the floor, much like a giant suitcase, renders it essentially dead weight. It significantly increases the car's overall mass, which in turn necessitates an even stronger and heavier chassis just to adequately support the combined load. This creates a detrimental spiral. You end up requiring more battery capacity to propel the additional weight of the chassis, which subsequently makes the battery itself heavier, thereby demanding an even more robust chassis once again. Tesla famously attempted to interrupt this cycle with an ingenious approach. Instead of meticulously stamping and welding dozens of individual steel components, they began injecting molten aluminum into enormous molds to produce vast, single-piece sections of the car. They termed this innovative method gigacasting. Instead of 60 discrete parts laboriously welded together, the process yields one monumental piece directly from the mold. This translates to fewer joints, reduced weight, and dramatically faster production cycles. It represented truly revolutionary thinking, but it harbored one colossal hidden problem intrinsic to the metal itself, a challenge that effectively prevented every other manufacturer from replicating it successfully. And it is precisely in solving that problem where Xiaomi's groundbreaking story truly begins. The oven problem that stymied everyone. When molten aluminum is poured into a mold and allowed to cool, the metal solidifies, but its internal structure is surprisingly weak. At a microscopic level, the tiny crystal structures that form the metal are often jumbled and oriented in random directions. The resulting part might appear perfectly solid, but when subjected to genuine stress, it becomes susceptible to cracking or deformation. The conventional solution to this fragility is known as heat treatment. This involves placing the cast part into a massive industrial oven and baking it at extremely high temperatures for several hours. This critical process realigns those minuscule crystal structures, transforming the part from brittle and weak into something robust and tough. It's an apt analogy to consider the difference between raw dough and a fully baked loaf of bread, identical ingredients, yet yielding a completely different, structurally superior result. Sounds straightforward, doesn't it? Herein lies the brutal catch. When a massive, intricately shaped piece of metal is subjected to such extreme temperatures, it doesn't just gain strength, it also physically moves. It warps. It twists in ways that are tiny but critically important for automotive precision. In the context of building a car chassis, where every millimeter of precision is paramount, even a minor bend means that crucial components no longer align correctly. Doors might not close with perfect fit, suspension mounting points can be thrown off, and the entire assembly becomes an engineering nightmare. Consequently, manufacturers found themselves trapped between two undesirable choices. They could skip the heat treatment, resulting in a part that maintained its correct shape but lacked the necessary strength to withstand real-world stresses. Alternatively, they could perform the heat treatment, producing a strong part that was, however, slightly distorted. It was a classic pick-your-poison dilemma. Every major automaker invested significant resources attempting to circumvent this fundamental issue. None succeeded. Some dedicated years to intensive research. Most eventually resigned themselves to the compromise, adapted their manufacturing processes to accommodate this inherent limitation, and simply moved forward. It quietly became one of those industry problems largely considered unsolvable. Xiaomi, however, observed this predicament and flat out refused to accept it. Their engineers meticulously examined every existing aluminum alloy available on the market. Not a single one could simultaneously satisfy all their stringent requirements: strong enough, flexible enough, dimensionally stable enough, and crucially, heat treatment free. The perfect alloy, it turned out, simply did not exist. So, instead of merely selecting the least bad option from the shelf, Xiaomi made a pivotal decision. They would invent the precise alloy they actually needed. And the method by which they achieved this feat is arguably one of the most fascinating aspects of this entire narrative. The AI that invented a new metal. This is where the story truly ventures into the realm of the extraordinary. Xiaomi developed a sophisticated deep learning AI system, which they aptly named Material Genome. Imagine this system as a tireless scientist that never sleeps, never grows bored, and possesses the capability to execute millions of complex experiments simultaneously within a virtual computer simulation. They meticulously fed it every known piece of information regarding metals, alloys, and the intricate field of material science. Then, they assigned it a highly specific mission: to discover a formula for an alloy that was inherently strong, sufficiently flexible, dimensionally precise, and most critically, required absolutely zero heat treatment after casting. The AI then embarked on an astonishing journey, running simulations for 10,160,000 distinct alloy combinations. This number is almost impossible for the human mind to fully grasp. To put it into perspective, if a human chemist were to test one new alloy formula every single day without ever taking a day off, it would take them over 27,000 years to explore that many combinations. The AI accomplished this monumental task in a mere fraction of that time, meticulously testing various mixtures of aluminum, silicon, magnesium, and rare earth elements across billions of virtual scenarios. Its objective: to isolate the one perfect combination that precisely hit every single target simultaneously. Consider it this way. Picture yourself attempting to bake the absolute perfect chocolate chip cookie. But instead of testing a dozen or two recipes over a few weekends, you simulate 10 million different recipes within a computer. This simulation accounts for every conceivable variation in ingredient ratios, precise baking temperatures, and critical timing. And the computer, with unfailing accuracy, provides you with the exact recipe that guarantees perfection every single time, long before you even consider preheating your oven. That fundamentally is what Xiaomi achieved. Except instead of cookies, they optimized the molecular structure of a brand new metal. The groundbreaking result is an alloy they call Titan's metal. It is a fully patented material, exclusively belonging to Xiaomi. When this metal cools after being cast in a mold, it emerges already possessing its full strength, already at the exact right dimensions, and immediately ready for assembly. No oven, no warping, no compromise in form or function. In practical terms, this innovation means that Xiaomi's manufacturing line operates at an accelerated pace, consumes significantly less energy, and produces parts with an unprecedented level of dimensional accuracy compared to anything relying on the traditional heat treatment process. The parts fit together with unparalleled precision. The manufacturing tolerances are tighter than ever before. The entire system benefits immensely from this single revolutionary innovation at the fundamental material level. However, a groundbreaking new metal represents only half of the equation. You still require a machine capable of utilizing it to its fullest potential, and Xiaomi has engineered one that seems almost too advanced to exist in the real world. The machine that prints car chassis, Tesla's Giga Press, renowned for its staggering 9,000 tons of clamping force, was, upon its public unveiling, hailed by automotive journalists as pushing the very engineering limits of what humanity could construct. It is the kind of awe-inspiring machinery that leaves even veteran engineers completely silent when they walk into its presence. Xiaomi, not to be outdone, has constructed an even more formidable 9,100-ton version, which they have aptly named the Hypercasting Machine. This isn't merely a slightly larger number on a specification sheet. The Hypercasting Machine commands an immense footprint, covering an area equivalent to 2 basketball courts placed side by side. It weighs over 1,000 tons on its own. It heats Titan's metal to a searing 700 degrees Celsius and then injects it into a precision mold at such incredible speed that air bubbles literally have no time to form within the metal as it rapidly fills the cavity. This seemingly minor detail about air bubbles is far more critical than it sounds. Air bubbles trapped within cast metal are akin to invisible internal cracks. From the exterior, the part might appear flawless, but when subjected to the extreme forces a high-performance car endures, these hidden voids become the critical starting points for catastrophic fractures. By employing injection speeds that are too rapid for bubbles to coalesce, Xiaomi achieves parts with an internal density typically only observed in highly specialized aerospace components. Every single cubic millimeter is solid uncompromising metal. Now, let's consider what this colossal machine actually produces during a real production run. The rear floor section of a car is one of the most structurally vital parts of the entire vehicle. In a standard car, that critical section is typically composed of 72 separate stamped steel parts, meticulously held together by 840 individual weld points. Each of those distinct parts must be manufactured separately, transported, stored in inventory, individually picked up, precisely aligned, securely clamped, and then welded one by one. The complete process consumes several hours and demands the involvement of numerous workers and multiple machines. Xiaomi's Hypercasting Machine, by contrast, produces that exact same section as a single monolithic piece in a staggering 100 seconds flat. 72 individual parts are consolidated into one part. 840 welds become 0 welds. Hours of laborious work are compressed into a mere 100 seconds. On top of this remarkable efficiency, the single-piece cast section is a substantial 17% lighter than its traditional multi-part steel counterpart. Furthermore, it generates 2 decibels less road noise, primarily because there are no tiny gaps or imperfect welds vibrating against each other at modern highway speeds. And once the machine produces each piece, the work doesn't stop there. Every single casting undergoes immediate, rigorous inspection, using X-ray imaging and high-precision laser sensors, all performed right within the machine before it even leaves the press. If the AI system overseeing quality control detects any flaw whatsoever, the part is automatically rejected and recycled before a human being ever lays eyes on it. The quality standard enforced is essentially superhuman, as no person could inspect at such an intricate level of detail with such incredible speed. A brand new chassis section rolls off this astonishing machine every 90 seconds. Now, if you believe that this casting process is the most impressive aspect of this entire story, what Xiaomi has accomplished with the battery will genuinely astonish you. The battery that became the car's bones. In nearly every electric vehicle on the road today, the battery pack is fundamentally a giant, expensive, and heavy box merely bolted underneath the car's floor. It sits there, performing one primary function: storing electricity. It offers no structural support to the car, nor does it contribute to the overall stiffness of the vehicle's framework. It simply exists as dead weight that happens to power the motors. Xiaomi posed a question that, on the surface, sounds simple but ultimately proved to be invaluable. What if the battery wasn't just a passenger? What if it was the skeleton? This revolutionary concept underpins CTB technology, which stands for cell to body. Instead of a discrete battery box attached to a separate frame, the individual battery cells are directly integrated into the chassis structure itself. The upper surface of the battery pack ingeniously doubles as the actual floor of the cabin, precisely where occupants rest their feet. The cells below are not solely dedicated to storing energy. They are actively contributing to holding the entire car together structurally. But Xiaomi didn't stop at mere CTB integration. They implemented one more design decision that initially sounds counterintuitive, but is in fact a stroke of genius. They flipped the battery cells upside down. Here's precisely why that seemingly small change matters so significantly. Every battery cell is equipped with a pressure relief valve, a small but crucial safety mechanism engineered to safely vent hot gas should the battery ever overheat. In a conventional battery pack configuration, these valves typically face upward, directly toward the cabin and the passengers. To safeguard occupants from the potential hazards posed by these valves, engineers are compelled to construct thick layers of protective material between the battery pack and the cabin floor. While absolutely necessary for safety, this protection inevitably adds undesirable height and considerable weight. When Xiaomi ingeniously flipped every cell upside down, the pressure relief valves now point downward, directly toward the road, safely away from the passengers. The essential safety protection is still very much present, but it is now handled by the inherent structure of the car's floor itself, rather than requiring additional layers of material packed into the batteries. This innovative approach allowed them to eliminate all those thick internal protective layers, bringing the total thickness of the battery plus floor system down to an incredibly slim 120 millimeters. That's roughly equivalent in thickness to a standard hardcover book. The ramifications of this single design decision are monumental. The car now sits substantially lower to the ground than most dedicated sports cars, which grants it an exceptionally low center of gravity. This, in turn, allows it to corner flatter and maintain superior grip through aggressive turns. Moreover, because the battery cells themselves are an integral part of the chassis' structural load path, the entire car achieves extraordinary rigidity. How rigid, precisely? The SU7 Ultra boasts a torsional stiffness of an astonishing 51,000 Newton-meters per degree. Here's a comparison that truly puts that number into perspective. A Ford F-150 Raptor, widely recognized as one of the toughest and most capable pickup trucks on the market, measures in at approximately 25,000 Newton-meters per degree. The Xiaomi sedan, remarkably, is twice as stiff as that robust trophy truck. It is also structurally stiffer than a Bugatti Chiron. A car conceived by a phone company utilizing its battery as its very backbone is more rigid than one of the most astronomically expensive road cars ever crafted. This exceptional rigidity isn't merely a cool bragging right or a trophy number for the spec sheet. It is the fundamental characteristic that enables every other system in the car to perform at its absolute best. When the chassis exhibits absolutely no flex under any load, the suspension components can execute their intended function perfectly every single time. The shock absorbers respond with precise fidelity to their tuning. The tires maintain a flat, optimal contact patch against the road surface even through hard cornering. The entire car behaves with the exact dynamic precision the engineers envisioned, precisely because its foundational structure never yields or moves unpredictably, and the engineers intended it to gracefully handle an immense 1,548 horsepower generated by 3 potent electric motors. Each motor spins at an incredible 27,200 revm, setting a new world record for a production electric motor. To provide a sense of just how fast that rotational speed is, most electric motors found in high-performance cars typically peak at around 20,000 revolution. Xiaomi's motors spin a staggering 35% faster, generating more power from a remarkably smaller and lighter package. This level of rotational speed enters the territory of jet turbines. Without the groundbreaking Titan's metal chassis, and without the ingenious CTB battery backbone, that immense level of power and such extreme rotational speeds would generate forces that would simply tear apart a conventional car structure over time. However, because the material itself, the sophisticated manufacturing process, the chassis design, and the innovative battery integration were all meticulously engineered together as a single interconnected system, every piece perfectly supports and reinforces every other piece. Asterisk what this actually changes. With the SU7 Ultra, Xiaomi has proven something far more significant than just producing one impressive car. They have conclusively demonstrated that starting entirely from scratch, unburdened by any preconceived notions about how things have always been done, can sometimes be the single most potent engineering strategy available. Using advanced AI to design a brand new alloy formula instead of merely refining existing ones represents a complete rewrite of the fundamental starting points. Constructing a casting machine larger and more powerful than any that previously existed, and employing it to replace dozens of individual parts with a single integrated component, signifies a wholesale rewriting of the manufacturing process itself. Flipping battery cells upside down so the battery can assume a critical structural load is, at a fundamental level, rewriting the very definition of what a car is. The Xiaomi Vision GT concept car, with its theoretical 900 horsepower and aerodynamic designs that would undoubtedly be banned in Formula One, is not mere science fiction. It serves as a tangible preview of what Xiaomi can already construct right now with the technology currently operational in their Beijing factory. Titan's metal is in active production. The hypercasting machines are churning out chassis sections every 90 seconds, and the CTB architecture is already in the hands of customers. What elevates all of this beyond a single company's achievement is the unmistakable signal it sends to every single automaker on the planet. The era of assembling cars from hundreds of individually stamped steel pieces, tenuously held together by thousands of welds, with the heavy battery simply strapped underneath like an afterthought, is definitively giving way to something entirely different. The new, emergent approach is to holistically design the material, the machine, the structural framework, and the energy storage system all together cohesively from the very inception of the project. This strategy allows advanced AI to uncover innovative solutions that human intuition alone would simply never discover. That isn't merely a better car, it represents a fundamentally different way of thinking about what a car is and how it comes into being. And rest assured, every serious automaker across the globe is paying extremely close attention right now. If you've made it this far, it's clear you share our passion for these cutting-edge developments. Please hit that like button, subscribe if you haven't already, and make sure to ring the notification bell so you don't miss what's coming next. We're committed to delving deeper into more next-generation engineering stories because the automotive and tech landscapes are poised for incredibly rapid transformation in the coming years. Now, here's the question we genuinely want you to answer in the comments below. Do you believe another major tech company, such as Apple, Samsung, or Google, possesses the capability to replicate what Xiaomi just accomplished and build a car from scratch that can genuinely compete at the highest echelons of performance and innovation? Drop your thoughts below and let's engage in a lively discussion about it.